All right, so let's continue our discussion of the initial rates method. Last time we said that what we do in the initial rates method is we run a series of experiments, at least two, okay? And for all these runs, we maintain the concentration, the initial concentration of all the reactants except for the one we're interested in, right? So, for example, if you look at this pair of experiments right here, experiment 1 and 2, you triple the initial concentration of B, you kept the initial concentration of A the same, and so what will these two experiments tell us? How concentration of B affects the reaction rate. And so if we measure the reaction rate for both of these experiments, suppose we find it to be 0.05 in both cases, then we figured that it's not affected by the concentration of B, so we say the reaction is zero order with respect to B. Okay? And if you compare experiments 1 and 3 then, okay, you can see that, I'm sorry, 2 and 3, actually it doesn't matter anymore. Now that we've established that B doesn't matter, right? If you compare 2 and 3 or 1 and 3, what happens? By doubling the concentration of A, what happens to the rate? From 0.05, it becomes 0.1, so that also doubles, right? So we say that the rate is directly proportional to the concentration of A, so we say that it is first order with respect to A. So that allows you to determine the order of the reaction, okay? So one last step in determining the rate law is to determine what the value of this K is, this rate constant. So what do you do with that rate constant? How do you figure that rate constant? All you have to do is go back to your data and plug in the numbers. So your initial rate, by the way, these are initial values, okay? So this is initial rate, that's initial concentration of A and B. So you plug in the initial rate for, let's say for experiment 1, you put in 0.05 moles per liter per second, that's your rate, is equal to K times the concentration of A for experiment 1 is how much? 0.1, right? So raised to the power 1. And the concentration of B for experiment 1 is 0.1, and that's raised to the power 0. So you can solve for K. How do we solve for K here? We say K is equal to 0.050 divided by, okay, that's moles per liter per second, divided by 0.10 molarity, moles per liter, times, what's something raised to the power 0? That's just 1, right? It doesn't depend on B. So this gives us how much? 0.05 divided by 0.1. It's going to be 0.5, right? 0.50. What happens to your moles per liter? Cancels out, right? So the unit here is just per second. You can see if the overall order is per second, you remember? The overall order is just per second. 1 plus 0 is 1, okay? Then the unit for your rate constant is just per unit time, per second or per minute, depending on what you're doing. And you can do the same for experiment 2 and for experiment 3, and you should get essentially the same number. Now, if you're dealing with real experimental data, though the K values you're going to get for each run is not going to be exactly the same, right? Because of random errors in your experiments. Okay, experiments are always subject to random errors. You don't always expect to get the same thing. So what you can do is you can plug in the numbers from experiment 1, experiment 2, experiment 3, and then take the average. Okay, that would give you your rate constant. Now, a better way is to actually run more than just two experiments for a particular. Let's say you wanted to determine the order of reaction with respect to a particular reactant. It's better to run more than just two experiments, okay? So for example, let's say you have a reaction between X and Y, Z and Y, and you want to vary the initial, you're holding the initial concentration of Z constant, okay? So you just want to study how the reaction is affected by Y. So instead of just doing 2 experiments where you're changing the concentration of y, you can run a series of experiments where you have different concentrations of y. So 0.01, 0.015, 0.02, and so on. So that gives you a better way, a more reliable result. Okay. So if you look at your rate law, okay, remember our rate law is of the form rate equals k times concentration of z times the raised to the power, which corresponds to the order of reaction with respect to z, times concentration of y raised to the order of reaction with respect to y. That's your rate law, remember? So in all of these cases, we're going to be maintaining the same initial concentration of z. So this whole thing would just be a constant. Okay? So this is constant for all the runs. So if you take the log of both sides of this equation, log of the rate is equal to log of this constant right here plus y times the logarithm of y. Or you can use natural log if you want to. You can use base 10 log. Okay, why does this equation work? If you recall, what did we say? Okay, another review of logarithms. Log of a product of 2 numbers would be equal to log a. So log of a times b would be log of a plus log of b. Okay, so if you log of this product would be equal to log of this plus log of that. Okay, and this is log of y raised to the power y. So these are very important identities for you to remember. Log of a to the power x, which is the same thing as x times log of a. Okay, so you need to remember this from that. Okay, so what we did here, when we took the log of y raised to the power y, we moved the exponent from for the concentration of y, we move the exponent in front of the log. Okay, so if you look at this equation right here, what do we see? You have a quantity, log of rate, which can be calculated by multiplying the log of y, another quantity. So these are the 2 variables, okay, by a constant. That's the order of reaction with respect to y. That's a constant, and then adding another constant. In other words, this is the equation of a straight line. This is what you call y equals intercept plus slope times x. Y equals mx plus b. All right, so if you were going to plot log of rate versus log of y, this is what you'll get. From this data that I'm showing you here, if I plot log of rate versus log of y, you'll notice your data points are going to fall in a straight line. Of course, if you were doing this experimentally, using real experimental data, there will be some scatter in your points. So what you do is you draw your best fit line. In this particular example, I just made up these numbers. You find that your expression says y equals 2x plus 2.301. So here, your coefficient of x, that's your slope, it turns out to be equal to 2. What does this tell you? That the order of reaction with respect to y is 2. That's your slope right there. Okay? So the slope of the plot will give you the order of the reaction with respect to the reactant you're interested in. Okay? Can we easily see that from this data? Can we just eyeball our data and see that it's actually, in fact, second order? The quickest way to do that is to look at what happens when you double the concentration of y. From 0.01 to 0.02, what happened? It becomes 4 times larger. From 0.02, it became 0.08. So 2 squared would be 4. So just by eyeballing your data right here, you can say it's second order. Okay? But this is what you would do using experimental data. Like I said, if you're looking at real experimental data, it won't be, it may not be as easy to spot to figure out the order by just looking at the numbers. Okay, unless you look really closely and think hard about it. All right. So that's the initial rates law. Okay, initial rates method. Let's take a look at another way of determining the rate law for the simplest types of rate laws. Okay, we're going to look at rate laws where the rate is just equal to some constant k, your rate constant, times the concentration of R raised to the power n. So we're going to look at specific special cases where the rate law depends only on one reactant, okay, and it is nth order with respect to that reactant, where n is equal to 0, 1, or 2. Because this is the most common type of rate law you would encounter, and we can also devise strategies so that when we run our experiment, the rate laws can be simplified into this form. Okay, so if n is equal to 0, okay, what you'll find is a plot of r versus time is going to turn out to be equal to linear, and the slope is equal to negative c times k. Okay, and where does that come from? Remember, the rate of reaction is 1 over the coefficient of r, right, times the rate of consumption of r is equal to k times, if n is equal to 0, what would that be? And you say that's equal to k times r raised to the power 0, and that r to the 0 is just going to drop out. Okay, this is what's called in math a differential equation. This thing right here. Okay, and when you solve this differential equation in math, you get a function. It tells you the solution to this will tell you how r depends on time. Okay, so r, you have two variables here, r, concentration of r, and time. Everything else there is a constant, and it involves what's called a derivative in math. And so when you solve this, the net result is you're able to figure out how r depends on time, how one variable depends on the other. Okay, so we're not going to go into detail as to how that's done. That you'll learn that when you do calculus. Okay, but the net result is that r is equal to some constant, c times k, times time, plus another constant, r naught. Okay? So that's the equation that you'll get. And we're going to examine that equation in a little bit more detail in a little while. If n is equal to 1, okay, so the rate of reaction is 1 over the coefficient of r times the rate of consumption of r is equal to k times r raised to the power 1. Again, this is the differential equation, and if you solve that differential equation, you'll find that natural log of r would be equal to some constant times time plus the natural log of r naught. R naught is just the concentration of r at time 0. So that would be your initial concentration of r. Initial concentration of r. Okay? Similarly, if n equals 2, okay, the rate of the reaction would be equal to 1 over the coefficient times the rate of consumption of r is equal to k times the concentration of r squared, second order. Okay? And if you solve this differential equation, this is the expression you'll come up with. 1 over r equals a constant times t is time, plus 1 over r naught. Okay? So these are the expressions that you'll find. And I've written these expressions in the form that will allow you to see immediately what you can do to get the values for the rate constant. Okay? Now, c, like I said, here is the coefficient of r in your balance equation. Unless otherwise specified, we're just going to assume it's c is equal to 1, okay? Because we can always adjust our coefficients for the balance equation so that the coefficient for a particular reactant is equal to 1. All right, so from now on, we can just ignore that c. We'll just take that as 1, okay? So let's see what the consequences are of these. Let's go back to... Let's go back to this expression for 0 order, okay? You'll notice here, this is equal to, if I were to plot r versus time, okay? Then you can see, I'm going to putting my r in my y-axis, so I can identify t as my x on my, I can put t on my x-axis, okay? So I can identify negative ck as the slope of my line. So y equals mx plus b, right? So ck would be the slope of my line, and like I said, we're just going to say c is 1. So negative k is the slope of my line, and b is my y-intercept. So if you make this graph, uh, let's see, if you plot r versus time, if it's zero order, you get, if you plot your data, you're going to get a graph that looks like this. It's going to be a straight line, and the intercept, when time equals 0, the value of r is r naught. And if you were to measure the slope of this line, you'll find that that slope is equal to negative k. You'll get a negative slope, okay? And k is your rate constant. We're just going to assume, like I said, we're going to assume c is equal to 1, okay? So your slope is equal to negative k. So that's a consequence of, that would be what you would expect if your rate law is zero order with respect to concentration of R. What would you expect to see if it is first order? If it's first order, then what you'll find is this. First order, I'm going to rewrite the equation for first order. So for n equals 1, we say ln of R equals negative kt plus ln of R naught. Okay? That means if you were to plot natural log of R on your y-axis and you plot t on your x-axis, then the slope you'll get is equal to negative k, so that's going to be your slope, and your y-intercept is going to be ln of R naught. So if I had data, okay, if I have R versus time, your data is actually going to look like this. R versus time is going to look like that. It's not going to be a straight line, okay? It's going to approach 0. It's going to be a curve. This is first order, n equals 1. But if I were to plot natural log of concentration of R versus time, what I'll find is my data is going to fit a straight line. All my data points are going to line up, and if I were to take draw the best fit line through my data, I'll find that my slope is equal to negative k, okay, and this y-intercept will be the natural log of R at time 0. Okay, so that's how you can tell that your reaction is first order with respect to reactant R. Okay, how can you tell if it's second order? This last one right here. So n equals 2. If you were to plot for n equals 2, again, if you plot R versus time, you're going to get a curve. Okay? Oops. R versus time will give you a curve. Okay? So it's not a quicker way to check whether or not it is second order is to plot 1 over R. So 1 over concentration of R versus time. And what you'll find is if it happens to be second order, when you plot your data, what you'll see is that these data points, 1 over R versus time, are going to fall in a straight line. Okay? And your slope is going to be equal to k. Why is that? Because what's your equation? 1 over concentration of R equals kt plus 1 over concentration of R at time 0. So in other words, if I were to put this on my y-axis, 1 over R, that's my y, and put t on my x-axis, then I'll find that my slope will be equal to k, right? And my y-intercept is equal to 1 over R naught. So this thing right here, the y-intercept would be 1 over R naught. Okay? So, you need to plot concentration of R versus time. If it turns out to be a straight line, then you know what? If it turns out to be a straight line, then you know it's zero order. Okay? Basically, what this is saying is dr dt, the change in R over change in time is a constant, so it doesn't matter what your R is. If it doesn't turn out to be a straight line, it's going to look like a curve. Okay, then you say it can either be n equals 1 or n equals 2. It can either be first order or second order. The way you can tell You should plot natural log of r versus time. If that graph turns out to be a straight line, then you know it's first order. If that doesn't turn out to be a straight line, you can try plotting 1 over r versus time. And if that turns out to be a straight line, then you know it's second order. Okay? So let's take a look at these examples right here. Here's a plot of, here's the same reaction, data from the same reaction plotted 3 different ways. This plots r versus time. This one plots ln of r versus time. This one plots 1 over r versus time. Okay, so this is r versus time, ln of r versus time, and 1 over r versus time. So based on what you're seeing on the graph here, is the order of the reaction 0 order, first order, or second order? Based on which graph is linear, you can tell whether the reaction is 0 order, first order, or second order. Okay. Which graph is linear? The natural log plot is linear, so it's first order. Okay? If this was linear, then you would say it's first 0 order. Okay? Now, a very important warning about doing this in the lab. You'll notice that if you do not follow your reaction far enough, let's say you stop your reaction after this much time has elapsed, you might think it's linear. That graph is linear, right? So make sure you follow your reaction far enough so you can tell if it really is linear. So sometimes you could be tricked into thinking something is linear when in fact it's not. It just so happens you did not follow the reaction far enough. Okay. In general, you should at least follow the reaction so that your R has dropped by at least 75% or more. Okay. So what that means, it's been cut in half at least twice. Okay. So if you start off with a concentration of 1 for R, follow it until at least it's down to about 0.25. That way, you can really tell if it's in fact a linear plot or not. Okay. Like even here, if you look at this part right here, if you didn't go far enough, you might think that that graph is linear. That graph might look like it's linear. Okay, so this one is first order. Okay, so here's a plot of natural log of r. So this is ln of r versus time. Is this 0 order, first order, or second order? Natural log, first order. Okay, the natural log plot is linear, it's first order. What's the slope here equal to? Negative k, right? So how do you estimate negative k from the graph shown? Let's calculate our slope. How do we calculate our slope? Rise over run, right? Okay, let's look at our numbers here. By how much did it drop as you go from 0 to 2? So our run is 2, right? 2 minutes. It went from, what's that number right there? That's negative 1, so negative 0.2, 0.4, 0.6, 0.8. So that's about negative 0.7. Okay? And so this is negative, and what is this number right here? This is negative 4, and that's negative 5. So 4.2, 4.4, 4.6, 4.8. So that's about negative 4.7, right? So negative 4.7 minus negative 0.7 divided by 2 minutes minus 0, right? That's your slope. And what would that number be? Negative 4.7 minus negative 0.7 is how much? Negative 4.0. Okay. And what's the unit for the numerator? What's the unit for concentration of R? Moles per liter, right? So think of it this way. Our numerator would be natural log of R at point number 2 minus natural log of R at point number 1, right? You pick 2 points. So let's call this point number 2 and point number 1. This is like y2 minus y1. That's your rise, correct? So what would be the unit for the difference of 2 logs of the same type of quantity? Remember your identity? Natural log of A minus natural log of B is equal to 1. The difference of 2 logs is equal to the log of the quotient, right? So that's the natural log of A over B. So this is going to be natural log of R2 over R1. So what's the unit for your numerator then? Concentration over concentration. So what's the unit for this thing? Unitless, right? A concentration term divided by a concentration term. So this is unitless. So anytime you plot logs, okay, and when you're calculating changes along that scale, the change along that scale will be unitless. So this is unitless up here, okay? So this number has no unit overall, okay? So the unit for this is so the unit for the whole thing for the slope is just -4 per minute, since the denominator has a unit of minutes. So that's your slope. So what's your rate constant for this? K would just be equal to negative of the slope, and your rate constant is always going to be a positive number. So negative of negative 4.0 per minute. Okay, so that's going to be equal to 4.0 per minute. Okay, as expected for a first order rate law, okay, for an overall first order reaction, the rate constant has just units of per unit time. Okay, what's the order of the reaction here? I'm plotting 1 over R versus time, and I'm getting a straight line. Second order. Okay, and what's my slope equal to here? Slope is equal to K. Remember, for a second order rate law, your reaction is 1, your equation is 1 equals 1 over R naught plus KT. Okay, so this is your X, that's your slope, that's your B, and that's your Y. Alright, so how do we determine the rate constant from here? How do you determine the slope? Rise over run again, right? So let's pick 2 points. Let's pick this point right here. What's that number right there? So that's going to be our point number 2, and this is going to be our point number 1. So slope equals y2 is what? That looks like a 10 right there. Okay, so 10. And what's the unit for my numerator? Let's do that later. What's my y1? Looks like a 2, right? So 10 minus 2. And the unit for the numerator is what? It's 1 over R. R is moles per liter. So what's the unit for 1 over R? Reciprocal. So it's going to be liters per mole. Okay? And what's my denominator here? What's my run? This one's at 2 minutes minus 0 minutes. And so my unit for my denominator is minutes. Okay? So 10 minus 2 liters per mole over 2 minus 0 minutes. That should give me 5 divided by 2. I mean, not 5 divided by 2. 8 divided by 2. That's 4, right? So that's liters per mole per minute. Or per molarity per minute. Okay, so that would be the rate constant for that reaction. Okay. Continue. Another way you can determine the rate law, okay, if for this simple rate laws, if its rate is equal to K times the concentration of R raised to the power N, okay. Actually, it's going to be, yeah, and we're just going to assume a coefficient of 1, okay. So let's just get rid of these C's over here. That's a coefficient in a balance equation, so I'm just going to get rid of that, okay. So if the rate is equal to K times concentration of R raised to the power N, okay, you can use what's called a half-life analysis. By plotting R, the concentration of R versus time, and you examine what's known as the half-life, you can actually determine your rate law, and you can determine what the value of your rate constant is based on the half-life. Okay? So the half-life is the time it takes for the concentration to be cut in half. Okay? In the case of a zero-order reaction, okay, you'll find that the half-life gets longer, okay? I'm sorry, it gets shorter it gets shorter the more the reaction has progressed, okay? As the concentration of R drops, your half-life drops. The time it takes for that concentration to get cut in half gets shorter, okay? Whereas if it's a first-order reaction, you'll notice that your half-life is a constant. Okay, it doesn't matter what your starting concentration is. It doesn't matter what concentration you're at. The time it takes for that concentration to get cut in half is the same. It's constant. That's how you can tell it's first order. Finally, if it's second order, n equals 2, you will find that the half-life is inversely proportional to the starting concentration. In other words, the higher your starting concentration, the shorter the half-life. So as the reaction progresses, what happens as the reaction progresses? Your concentration drops, right? So it's going to take longer for that to get cut in half. All right. So those are the consequences of these rate laws. Okay, so your half-life is, okay, this one, what happened? What did you say happened here? It gets shorter, right? As the reaction progresses. If it's first order, it's constant as the reaction progresses. If it's second order, it gets longer as the reaction progresses. Okay, so let's see what happens there. Let's look at this one. Based on the half-life here, what's the order of the reaction with respect to R? Is it 0, 1, or 2? Okay, how do you determine the half-life? Let's look at right here when the concentration is 0.01. What's half of 0.01? What's half of 10? 5, so 0.005. Okay, where is 0.005? Right here. So how long did it take to go from 0.01 to 0.005? 25 seconds. Okay, so when the concentration of R, if you start off at 0.01, your half-life is 25 seconds. Okay, now when my concentration of R is 0.05, what's half of 0.005? 0.0050, let's make it that way. What's half of that? Half of 50 is 25, so it's going to be 0.0025. Where would 0.0025 be? Here's 0.002, here's 0.003, 0.0025 is over here, and oops, what happened? Okay, 0.0025. Okay, that's 0.003 right there. So this is 0.0025. That's that one right there. So to go from 0.005 to 0.0025, how long did it take? 50 seconds, right? The half-life is 50 seconds. So when your starting concentration gets cut in half, what happens to your half-life? It gets longer. Okay, so we say the half-life is inversely proportional to the starting concentration. So is this thing zero order, first order, or second order based on the information I gave you earlier? Okay, it is second order. Okay, if as the reaction progresses, the half-life gets longer, it's second order. Okay. In fact, if you multiply half-life times the starting concentration, 25 times 0.01, okay, that's going to be equal to 50 times 0.005. Remember your Boyle's law? P1 V1 equals P2 V2. Whenever the product of two things is a constant, we say they are inversely proportional. So the half-life and the concentration are inversely proportional if the order of the reaction is second order. So if I were to ask you, what if I were to start at 0.008? Is my half-life going to be, okay, so what if I start up at 0.008 over here? Is my half-life going to be R equals 0.008 based on this data? Is my half-life going to be less than 25, equal to 25 seconds, or greater than 25 seconds? Or greater than 50 seconds? A, B, C, or D? Let's do that. What do you think is my half-life? Oops. What happened? Okay. It's going to be, oops. Okay. Let me elaborate on that a little bit. We've already established this is second order, right? The half-life gets longer the smaller your starting concentration, okay? So when I said my starting concentration was 0.01, what was my half-life? 25 seconds. So if it's 0.008, and we did what? 0.005, it was 50 seconds. What do you think this number is going to be in between? As the concentration drops, the half-life gets longer. So what's the best answer? Try it again. Okay, much better. Okay, correct answer is C. In fact, you can figure it out. What should it be? We're going to say 0.010 times 25 must be equal to 0.008 times x, right? But got half-life there. So what would the half-life be? X would be 0.010 over 0.008 times 25. What would that be? 31.25 seconds. Okay. 31.25 seconds. Let's see if that's in fact the case. Let's look at our graph. From 0.008, what's half of 0.008? 0.004, right? So that should be about 31 seconds approximately. Is that about 31 seconds? Yeah, that's a little longer than 25 seconds, right? So. Now, how do you determine the rate constant? Let's go back to our equation here. The rate constant, okay? And like I said, I'm just going to get rid of that C. If it's second order, from the half-life, you can get the rate constant. The rate constant, how do I solve for K here? K equals 1 over R naught times the half-life. Okay? So that would be the rate constant for a second order reaction. So going back to our example, what's our rate constant? Our rate constant is, our second order rate constant is 1 over R naught starting concentration times the half-life. Okay, so that's 1 over, what's our starting concentration? 0.010 moles per liter. And our half-life was 25 seconds. So that's equal to, what's 1 over 0.01 times 25? 0.01 times 25 is 0.25. So 1 over 1/4 would be 4, right? So this is going to be 4. And what's the unit for our rate constant? Per molarity per second. Okay? That's the unit for a second order rate law. That's your rate constant right there. So your rate law, we say, is, you write your rate law, you say rate is equal to the rate constant, which is 4 per molarity per second, times the concentration R raised to the second power. Okay, so that's how you can tell what your rate law is. Okay, let's take a look at this one. Based on the half-life, what's the order of the reaction with respect to R here? Let's see, how long did it take to go from 0.01 to 0.005? So when R is 0.01, what's our half-life? 25 seconds. How long did it take to go from 0.005 to 0.0025? So this is 0.002, that's 0.003, so 0.0025 is over here. How long did it take? If you're starting off at 0.005, how long does it take? Another 25 seconds, right? You have to start counting from where you start, from where you're starting. So it takes 25 seconds. So based on this information, is the order of the reaction 0, 1, or 2? Obviously, it's not 2, right? We've talked at length about second order. The half-life gets longer if it's second order. So is it 0 order or first order? It's first order. Okay. Going back and here. Okay. Look. It gets longer if it's second order. The half-life is constant. Okay. Let's get this out for you. The half-life is constant if it's first order. So in fact, what is our rate constant here? This is first order, so n equals 1 here. So how do I solve for my rate constant? It's just equal to natural log of 2 divided by the half-life. So from the half-life, I can figure out what the rate constant is. What's the value of natural log of 2? It's 0.693. So 0.693 divided by the half-life. Okay? So let's look at this one right here. What is our rate constant here? Natural log of 2 divided by the half-life, which is constant. So it's 0.693 divided by our half-life, which is 25 seconds. How much would that be? 0.693 divided, oops. Okay, here, by the way, if you want to know what ln of 2 is, 2, take ln of that is 0.693, okay? So ln of 2 is 0.693 divided by 25 seconds, that's 0.0277, 0.028, okay? And then what's my unit for my first order rate constant? Per unit time, so per second. So you'd say the rate law for this reaction is rate equals 0.028 per second, that's my K, right, times the concentration of R raised to the power 1. That's my rate law. Okay. Let's apply what we've learned so far to this question. The rate law for a reaction is rate equals K. Okay, what's the order of the reaction here? N equals 1. I have reactant A, so it's rate equals K times reactant A raised to what power? If A doesn't appear here, 0 order, right? So N equals 0. Okay. If it takes, so what's the equation that's applicable to this? Concentration of A would be concentration of A naught minus KT, right? So that's the equation that's applicable there. You know that if it's 0 order, then concentration of A versus time is going to be a straight line, and the slope of that line is equal to negative K, right? So if it takes half a second for the concentration of reactant A to drop from 0.1 to 0.05, how long will it take to drop from 0.05 to 0.025? What's the value of K? We can go back to our equation for the half-life. Okay, the half-life for 0 order, okay, is this one right here, and just get rid of that C right there. So your half-life for a 0 order is just initial concentration over 2 times the rate constant. Okay, so our half-life is initial concentration over 2 times the rate constant. Okay, so let's see. Our half-life is the initial concentration of A over 2 times the rate constant. Okay? Starting concentration of A over 2 times the rate constant. So I can solve for K, can I? Now, let's look at this question. It says it takes 0.5 seconds to drop from 0.1 to 0.05. So from 0.1 to 0.05, that's a half, right? So that must be the half-life. That's my half-life if my initial concentration is 0.1. Right? So I can solve for K. So if my initial concentration is 0.1, my half-life according to the problem is 50 seconds. Is that 50 seconds? 0.5 seconds. Can I solve for my rate constant here? My rate constant is going to be equal to A over 2 times the half-life. What would that be? 0.100 moles per liter over 2 times what? 0.50 seconds. So what's my rate constant equal to? 0.1 over 1. It's 0.1, right? So this is going to be 0.10 moles per liter per second. That's my rate constant. Okay? 0 order. So how long will it take to drop from 0.05 to 0.025? if I've cut my starting concentration to half of what it was, is it going to take longer or shorter? Zero order. Second order, it gets longer the further the reaction goes, right? First order, it stays constant. Zero order, it gets shorter. So I'm starting from 0.1, now I'm starting from 0.05. So if it took half a second when I start from 0.1, how long will it take to get cut in half if I start from 0.05? It gets shorter, okay? So we say the half-life is directly proportional to the starting concentration, okay? Your half-life, since it's zero order, is directly proportional to the starting concentration. So if I'm starting from 0.05, it's only going to be 0.25 seconds, okay? So you can say, to solve this problem, you can say that 0.50 seconds is to 0.1 moles per liter, as 0.05 as x is to 0.05 molar. Okay, and so x is going to turn out to be 0.25 seconds. The half-life gets shorter. Okay, and you can solve for your k. We did that earlier. Here's another way you could have done it. You could have said, all right, I've solved for my k, and I say a is equal to a naught minus kt. Okay, then I can solve for when what would be my half-life when a is half of a naught, right? When a is equal to half of a naught, then my t is equal to my half-life. So you can say 1/2 a naught equals a naught minus kt. Okay, and you can see where that formula for the half-life comes from. So k, let's solve for half-life here. The half-life is equal to a naught minus 1/2 a naught over k. So that's just a naught over 2k. Right? So that's where that equation comes from. Let's try this one. Again, zero order. Takes half a second to go from 0.1 to 0.05. How long will it take to go from 0.08 to 0.04? You're cutting it in half, right? Both cases. Is it going to be shorter than 0.5 seconds or longer than 0.5 seconds? Let's do that first. Is it A going to be shorter than 0.5 seconds? Is it still going to be 0.5 seconds, or C, is it going to be longer than 0.5 seconds? You know, knowing that this is zero order. So it's going to be shorter. How much shorter? Proportionately shorter. Okay, so you can say 0.5 seconds is to 0.1 moles per liter per minute, as x is to 0.080 moles per liter. Okay, and so that's going to be equal to how much? 0.4 seconds. Okay, it's proportional. The rate law for reaction is rate equals K. It takes half a second for the concentration to drop from 0.1 to 0.05. What would be the concentration of A? What would the concentration of A be 1 second later? Let's solve for K first. What's our K again? This is zero order, so K is equal to starting amount, which is 0.1, right? So it's equal to A naught over 2 times the half-life. So A naught is 0.100 moles per liter over the 2 times our half-life is 0.5 seconds. So what is 0.1 over 2 times 0.5? Should be able to do this in your head. 2 times a half is 1, right? So you're dividing by 1. So this is 0.100 moles per liter per second. That's our K. So we can then say that A must be equal to A naught minus KT. Okay, this is the equation for zero order. Okay. So what would be the concentration 1 second later? All I have to do is plug in my A naught here. What's my A naught? 0.100 moles per liter minus my K. What's my K? 0.100 moles per liter per second. 1 second later, 1.0 seconds. That cancels out. So what would be your answer? 0.1 minus 0.1, 0. Okay. Now, word of caution: reactions, the zero order reactions don't actually stay zero order forever, because if they do, then they react after this, it's going to go negative, right? And you can't have negative concentrations. In fact, zero orders typically tend to just be to have a limited range. After a while, the graph of our concentration of A versus time, instead of that being a straight line, actually it tends to curve. Okay, so this is the prediction if the trend were to continue. What do we know about reaction concentrations of reactants? Eventually, they would level off. Okay, so they're not just going to continue going down linearly. Okay. Let's take a look at this one. This might be a good time to take a break. Huh? Okay, so let's pause this one.